This is the fourth video in a lecture series as part of a class on single agent search being taught at the University of Alberta. And this lecture is going to be looking at heuristics. So today we're going to look a little bit about heuristics, where they come from, and at least one way of where they come from, and some of the properties that we require on top of our heuristics. And there'll be a lecture after this one that looks at how we use heuristics in algorithms themselves. And to motivate the lecture, or the beginning of the lecture today, I'm actually going to begin with a video. And so we can look at this video here of a very simple map. And in this map, we're going to have a start state, which is going to be on the right-hand side, a goal that it's searching to. And what we're going to do is first we're going to watch what happens when we do a Dijkstra's algorithm search on this map. So this is the search going out. The red states are in the closed list, the green on the open. And what you see is, as we're trying to find the path from the start to the goal using an uninformed search algorithm, it searches in all directions out towards the goal. And we've reached the goal, but it basically has no notion of where the goal is. But we see in a two-dimensional map like this, obviously, we have a sense of the direction that we could go towards the goal. And so it's really a waste of time to go in all directions at the same time. So if we solve this exact same problem using a heuristic, we could try and be guided in the direction of where the goal is. And we're going to do just a very small fraction of the work that it would take, given the extra information of some guidance, which in our case is going to be a heuristic. And so what we're going to look at today is what are some of the properties we want on top of our heuristics, and then we'll put them into practice in the lecture following this. Okay, so we want to talk about heuristics, and so we want to answer, the first thing we're going to think about is, what is a heuristic? And so we'll look at that. We want to know, where do they come from? And then we'll look at properties. So those are the three pieces we'll be looking at in this lecture. And when I answer this question today of where do they come from, what we're going to see here is one answer of where they come from. And but there's many other answers, and in part of this course, what we'll be doing is looking at other ways that we can create heuristics and how we can get different strength heuristics or the properties of a domain that influence where our heuristics should come from. Okay, so fundamentally, if we're answering the question of what, then what it is it's a distance estimate. That is, it's going to map a state into a real number that's going to give us something that's a distance. And so we're going to write this. Actually, we're going to write here, we want h of s is going to be mapping to some sort of real number that is telling us our estimate of the distance from s. So sometimes I can just say s implicitly. There's a goal here. Sometimes I'm going to write the goal explicitly, and sometimes I'm not. And so we're going to define a function h star of s. And this is going to be the perfect heuristic, or the exact cost of s to the goal. Or exact here would be the optimal cost, again, depending on your cost function or something like this. So ultimately, heuristics are numerical calculations. And that's important because a little bit later in the class, we'll talk about constraints. And constraints are something that haven't been talked about explicitly everywhere that they're used, but constraints are not numerical calculations. Okay, and so if we think about several different domains, we could think about the distance estimates that we might use, and we can think about where those come from. In particular, so we'll come back to what are the properties here, but where do they come from? Where do we get them? And we're going to look at several different examples here, but the basic answer, particularly heuristics that don't require any pre-computation, although some of the ones we look at here will require pre-computation, They come from, one way that they can come from is a relaxation of the original problem. And let's look at some examples of this. Yeah, so this is where many common heuristics from, or also another one we're going to look at comes from just basically the simple properties that we find upon a domain. So maybe we can reason about invariance of our original domain. Okay, so let's look at an example. So let's suppose that I'm doing pathfinding. Okay, and when I'm doing pathfinding, what I'm going to have is I'm going to have start location. I'm going to have some obstacles here in the world that are maybe going to get in my way. And then I'm going to have a goal location. And if we think about the problem definition for pathfinding, what is the problem definition? Well, the problem says I need to get from the start to the goal, the actions that I have to go from a location in free space to another location in free space, and then I have to find a path through free space to be able to get to the goal. But what we might observe is that we could relax the constraint that we actually have to move through free space. And we could say, well, maybe we can just pretend that I don't have to move through free space. And then what I would see here is in that case, of course, I would be able to move directly from the start to the goal. Now, if I'm allowed to move arbitrary angles, I get something like that. If I'm forced to be moving on, for instance, an 8 connected grid that can go to the 4 cardinal and the 4 diagonal directions, then I might get a path that looks something like this. Okay. But regardless, we can think of this as I've got this constraint of normally I'm not allowed to move through obstacles. And if we relax that constraint, then we can see I can just take the distance between the two locations, the start and the goal, whether it's in sort of an octile distance or a straight line distance. And once I do that, I'm going to get an estimate of the cost. And adding constraints to the problem is only going to make it more difficult. This is a very easy computation that I can make. And so this is something I could use as a heuristic. And we're going to talk about the properties and sort of why this sort of relaxation of constraints gives us the properties that we want in a moment, but we'll get there. So another example would be to think about let's think about the sliding tile puzzle. Okay, so if we think about, I'm going to I call that the STP, and we'll think about a very simple version of that STP. And I have some arrangement of tiles, 3, 4, 5, 6, 7, 8, and then I have a blank here. And if I think about the sliding tile puzzle, I can think about writing down what are the constraints that exist here. So I could think about, I have an operator called swap that swaps something like A and B, and I would have some preconditions on swap. Precondition would be that, for instance, that B has to be blank. And we might have a precondition that says the A and B have to be adjacent. And then we have some postconditions or some effects. And those effects might say something like, now, once I do the swap, then blank A, because B was blank before. I'm not going to write it down here, but I would say, okay, well, B is not blank because we've made that move. And then we could have something like in B is in location A. Okay, in practice, you need a couple more things here to sort of have things that are deleted from the environment, and I'm not going to talk about those here. But if we look at these simple things, now we could ask the question, what if we relaxed the original problem? So let's suppose that we relax the condition of adjacency. Okay, if I relax the condition of adjacency, then what's going to happen? Well, in any move, what would I be able to do? I would be able to take any tile that's out of location. So normally this would be 0, 1, 2, 3, 4. So we could take the 4 actually, and I could just immediately move it. Well, I can move it to where the blank is. So if this is 0 to 8, I can take the 8, and I would just be able to move it there in one step. Now the blank is here. And so I could immediately take, well, my numbers here aren't great. I could immediately move the 5 there. The blank would be here. I could immediately move the 3 there because they don't have to be adjacent. We'd still have to move into the blank, but we wouldn't have to be adjacent. And so this heuristic approximately would give you the number of tiles that are out of their locations, because in each time step I can move one tile into its goal location. And so that would give us, that's what we would get if we relax the adjacency constraint. Another constraint we might want to relax would be that we'd have to say that I'm going to swap with the blank. So maybe I'm not actually requiring me to swap with the blank, and essentially this would allow me to have two tiles to be in multiple locations, but we can basically move tiles through each other, but they still have to be adjacent. And so when we do something like this, what I can do is that I can just immediately and basically independently move every tile from its current location to the goal. And so when I do that, actually, so this is basically the number of tiles out of their location. And if I think about the blank, so I'm ignoring the blank, I can move tiles through each other. They don't have to move through the blank. Then this gives me what's called Manhattan distance. And what that means is that it's basically for every tile, I compute how many moves does it have to make to get to its goal. And once I compute that number of moves, then I can sum that up for all the tiles, and that would give me the total number of moves. Now, in a strictly, if I have a representation here that is represented by these predicates, then I might actually have to do a search to solve the heuristic value. But if we're thinking about, well, I do this analysis, I can write a program that iterates over or pre-computes these distances, and then we could look it up very efficiently. So because we're not using factored state representations, we're going to assume, well, we could actually just write this down, what it's going to be, or figure out a way to compute it. But we're going to come back and see a little bit later where Manhattan distance could actually come from. We could derive it in other ways. But here's another example here. Another example that we could look at would be what's called the Pancake Puzzle. And the Pancake Puzzle is a problem where you are a waiter. And so if I'm a waiter and I am bringing out to my customers a tray of pancakes, and what I want to do is I want to order them so that they look as nicely as possible. So you could imagine that I have a small pancake, and then maybe I have a big pancake, and then maybe I have a medium-sized pancake. And here I am, I'm walking, so I'm a waiter, I'm holding the plate in one hand, and then in the other hand, I'm holding a spatula. And what I can do is I can stick the spatula into the pile, and I can flip. So I could imagine sticking the spatula into here, and then I could flip that stack of pancakes. And my goal is that by the time I get to the table, that I would have all the pancakes laid out in an order such that they are they look something like this. That is, they're in sorted order. Okay, so that's the Pancake Puzzle. Lots of very interesting research that's gone on that problem. And here, what we can do is, instead of maybe trying to analyze the predicates that exist here, we could think about the conditions, or what happens when we take an operation. And what we can notice is this operation of taking a set of pancakes, in this case, like we take two pancakes and we flip them, that operation does not change locally whether a subset of pancakes is sorted. It only changes it at the point where we flipped, whether there's a sorting or not. And so if we looked at this one, if we flipped this, they would be in reverse sorted order, and then one more operation would allow us to get into this order right here. So what we can look at is that every time I flip a set of pancakes, what may happen is we may induce a gap here, or two adjacent pancakes that are not in sorted order. And every flip can at most add or remove one pair of pancakes that are out of order. And then when I look at the final stack, there's no pancakes that have an adjacent pancake that is that doesn't sort of adjacent in the sorted order. And so what that means is that in the Pancake Puzzle, we can count what's called the Gap Heuristic, which is just basically the number of gaps between adjacent pancakes. Okay, and what we see is that in the final state, there are no gaps. So that says it would be a heuristic of 0. That seems pretty accurate. In any other state, we know that each operation only changes one gap, and therefore that's going to be a nice heuristic that's going to get us to the goal. In fact, that's giving us the property of admissibility. It's not going to overestimate the number of actions. So why don't we go ahead and now start to define some of the properties that we have. So remember that up here we said that H star was the exact cost of a path between states S and G. And so we're going to go down here and we want to talk about properties now. Okay, so what are the properties that we want? The first one we often talk about is admissibility. And admissibility basically says we don't want our heuristic to be overestimating. We get in trouble if our heuristic overestimates. So what this is going to say, we could write this out a number of different ways, but we can say sort of for all, if we're only thinking about a goal, so I'm going to leave the goal implicit here, we could say for all states in my state space. So I'll just say for all S, this, well, could be for all S in some set of states in the state space. What we want to know is that H of S is less than or equal to H star of S. Okay, so if we know what the true distance is between a state and the goal, then we want this state to be less than or equal to that true distance. So this is the most common property that people think of, but usually we actually use a stronger property, which is called consistency. So a heuristic is assumed to be admissible and consistent. And consistent is really important, and so we're going to spend a little bit of time trying to understand this. But it's hard to maybe understand, like if I just write it down, I'm writing down some numbers. And so we're going to look at this, we're going to explore a little bit. I'm going to start with the undirected version of this. And the undirected version of this is that if I'm thinking about two states, A and B, then the heuristic of A minus the heuristic of B, if I think about, and for right now, we can think about two adjacent states, but we'll actually show that generalizes. So if I have two states A and B, and I look at the difference of heuristic, then this must be less than or equal to the actual cost to get from A to B. Okay, so we're going to let C of A and B be the optimal cost from A to B. And notice here the A and B, neither of these necessarily have to be the goal. We're still going to have to be less than the cost from A to B. And in this, this is what we get in an undirected graph. This is equivalent to a triangle inequality. But what we're saying here is if we look at the change in the heuristic, then the change in the heuristic has to be, between two states has to be less than the actual cost. Okay. And so let's draw what's going on if we think of this as the triangle heuristic. So, sorry, the triangle inequality. So I have some state here, A. I have some other state, B. And my heuristic is doing an estimate of the cost from A to B. Actually, let me, just to make it clear that these are estimates, I'm going to write this in red. So I've got some estimate to the goal state here. Okay. So we've got an estimate from A to B, and then what we have is we have this edge here, which is the cost from A to B. And what you see is that these two estimates plus this edge here form a triangle. And what the triangle inequality is basically saying is that, like, we actually have to be able to form a triangle out of this. So if we think about particularly stretching this triangle, then we can, the two ways that we can stretch it here is we can basically stretch it in this direction, or we can stretch it in this direction. Okay, I apologize, my lines aren't particularly straight here. Okay, we think these are the two ways that we can stretch this, and what we're saying is that when we're trying to estimate the, between two of these states and we get a change in heuristic, the change in the heuristic, if we're going to form a triangle, the change in the heuristic is bounded here, is bounded by the actual cost of the edge here. So we're saying we shouldn't be able to go beyond that. Now, this, why do I want something like this? It ends up that this is really motivated by the properties that we have when we do our actual search. And so let's just talk about that. If we think back to Dijkstra's algorithm, we had this property that what happened is as I went along the search in Dijkstra's algorithm, that the edge costs are always increasing. Okay. And what we want to see sort of equivalently, that is, as I'm doing a search in A star, which of course I haven't introduced that algorithm yet, but we want to see this equivalent property. And so what we're thinking about saying is, well, I'm at some state A here. Okay, so this is the undirected case. In the directed case, what we're wanting to see here is that we want to see something like this. So I'm going from an A to a B, and now let's consider that's a directed edge. So I can only go one direction from A to B. And okay, and then I have a, right, so I have the heuristic. So I'm going from A to B, and then I've got, of course, my goal down here. Okay, so what I want here is I want that as I go across this edge, that basically my costs or my estimates are not going to drop more than I expect. Okay, so we think about this is if I think here that I'm like 10 steps away from the goal, and if I take an action here that, so let's just say that's 10 steps away from the goal. I take an action here that says I'm going to take 3 steps along some path here. Okay, what I want to have happen here is I don't want to have, I suddenly find myself here that I've moved 3 steps. And now instead of being 10 steps from the goal, I think that I'm only 5 steps from the goal. Okay, this seems to be an inconsistency in the heuristic, right? Because I'm 10 steps away, I moved 3 steps, and now I'm only 5 steps away. But what can happen in the directed case is you could imagine that I'm sitting here, I'm thinking about moving from A to B, and it's a directed graph, so here I am, I'm wanting to get to the goal, sorry, and the distance here is 10, and I take a step that costs 3, and now what could happen? Well, what is allowed to happen here is that I suddenly find myself 20 steps away from the goal. Okay, so this is interesting because this isn't allowed in the directed case, but in the undirected case. But in the directed case, basically, I shouldn't take a step and find myself much closer to the goal than I thought I was, but I am allowed to take a step and find myself much farther to the goal than I thought. And so if you think about like, well, here I am, I'm on the freeway, and, I'm going towards the goal, and, if I just keep going on the freeway, maybe I'm going to get to my goal really quickly. But if I accidentally get off the freeway, you could imagine that in getting off of the freeway, I suddenly find myself that I can't get back onto the freeway for another mile. And now I've got to go a really long distance to actually get back on the freeway and continue my path. So that's a case here where what we have allowed is that I'm allowed to take an action and find myself much farther from the goal, but I'm not allowed to take an action and find myself much closer to the goal. Okay, so this is what happens for consistency in the directed case. And so what we're going to say here is, here I have h of a, or h from a to the goal where I was, and now what I'm thinking about is I'm going to take an action. So we can write this in a couple different ways, but I'm going to say the heuristic from the A to the goal must be less than or equal to the heuristic from B to the goal plus the cost to go from A to B. Okay, and so that just says that as I go from A to B in a graph, that the heuristic cost has to go up. It's not allowed to go, basically, plus this edge. I don't expect to see the heuristic cost or the total cost, which is the path that I traveled, plus the additional heuristic is not allowed to go down. Okay, now this doesn't necessarily correspond to the triangle inequality, because what it does say from the triangle inequality is it handles this case that says I can't get too close, but it doesn't handle this case to say I can't get too far. Okay. Okay, so this is a lot about consistency, but we're going to see that consistency is actually a big deal. There's a number of techniques that don't give us consistency, and if we don't have it it's going to be potentially a problem. And it's actually quite complicated what results when we don't have consistency. And so it's important that we get this correct. Okay, so now we can start to ask a question. Well, admissibility and consistency, how do they relate to each other? So remember, admissibility here is saying that the value of a state has to be less than, the heuristic of a state has to be less than the optimal heuristic. We have our two different versions of consistency here. And we want to think about, so there's a question here, sorry. Question, if a heuristic is consistent, does this imply, so I'm asking the question, does this imply that it is admissible? Okay. And this is something worthwhile to think about. You could pause it, the lecture, and think about that for a second. And the other question we'd want to ask is admissibility. If a heuristic is admissible, does this imply that it's consistent? Okay. And when we look at this, then we can answer both of these questions. So consistency and admissibility, it requires one other thing. This requires that if h of the goal is equal to 0, okay, if h of the goal is equal to 0 and the heuristic is consistent, then we can guarantee, that's not a question, it is a statement actually, that the heuristic will then be admissible. And the way we can see this is fairly straightforward. We'll look at the undirected case, but the directed case follows in the same way, is that, okay, the heuristic at the goal is admissible. And now we think about taking one step away from the goal. And what we know here is the heuristic is not allowed to change. The change in the heuristic from state A to B, where A in this case happens to be the goal, has to be less than the actual cost. So when I get to B, then the heuristic of B has to be less than the cost of the goal, which is exactly the definition of admissibility. Okay, and then you can think about following any path, any optimal path sort of backwards, or we'd want the forward path to be optimal, but if we're reasoning over it backwards, then we would see that for all those states, we would also that we would maintain this property. So, I take another step here. If the optimal path from C to the goal goes C to B to A, we know that the change from A to B was less than the optimal cost from A to B, and we know from B to C it was less. Then, of course, the sum of A to B and B to the C is less than the cost from A to C, and our heuristic will then still be admissible. With consistency, you can basically make the same argument. Okay, so we have the property that if I have a consistent heuristic, it'll always be admissible. And what we can see, for instance, if we go back and look at some of these heuristics, in the pancake puzzle, so that's the number of gaps between pancakes, every action has cost 1, and the heuristic can only add or remove 1 pancake, and the heuristic at the goal is 0, and therefore the gap heuristic we can see is going to be both consistent and admissible. If we look at Manhattan distance, so the Manhattan distance heuristic, the goal has a heuristic of 0, and every action costs 1, and the heuristic on every action is only going to move 1 tile, 1 location, which means the heuristic can only change by at most 1, and therefore the Manhattan distance is also going to be both a consistent and thus an admissible heuristic. And finally, if we look at pathfinding, we would see with pathfinding the same thing. When I take any one action in the world, we may have different edge costs here, but the heuristic can change at most the edge cost, and therefore pathfinding, like a straight line or an octile distance heuristic, will be consistent, and therefore it'll also be admissible because the heuristic of the goal is 0. Okay, so for all of these sort of very natural heuristics that we get here, they're going to be consistent, and therefore they're going to be admissible. Okay, and the other question then we want to answer is, well, is there an admissible that is heuristic? Does it imply consistency? And the easiest way to show that is, of course, we can show an example. So here I could have a state that will show, and let's use an undirected graph just to make this easy. Okay, we're going to start state here, and we can say, look, I'm going to make each of these states to be 10 away from the goal. I can make the, so what do I want to have happen? I want to say that the the question is, can I have an admissible heuristic that's not consistent? And the answer is yes. So I know here that, and I'll just call this node A. I know that I could have h of s is equal to 20, and I could have h of a is equal to 0, and then I can have h of the goal is equal to 0. Okay, so here this is admissible because h of s is 20, the actual distance is 20, so it's less than or equal. H of a is 0, and the actual distance is 10, so it's less than or equal to that. But if I look at the change in the heuristic across this edge right here, the edge is changed by 10, the heuristic has changed by 20, and therefore this is an admissible heuristic that is not consistent. Okay. Okay. And important is that consistency, the last thing here as this part of the lecture, is that a consistent heuristic, if it's consistent between all pairs of adjacent states, then you can show by induction that it'll be consistent over larger sets of states. We have to be careful. There's sort of two versions of this. So local to global consistency. Okay, so I can think about a path through this state, and any path I want to draw through that state space, or any simple path that I want to draw. And we know that, so if we know that along any one of these one edges, that the actual change in the heuristic is going to be less than the cost, then I can just sum this up over all these states, and I'm going to see the same property that, that the sum of the costs is going to be greater than or equal to the sum of the heuristics, the changes in the heuristics. But the only thing that I have to be careful about here is that if I draw a path and then I ask what happens over that path, that's fine. But if I want to just say, like, for any arbitrarily h of a and h of b, and I want to be thinking about the cost from a to b, where a to b is actually the optimal cost, then what I have to be doing is I have to be reasoning over actually the shortest path between these states. And so local consistency, like if I think about a path, I could reason over any path. But if I'm wanting to write the general equation, then this requires that I'm actually the path that I'm looking at is actually the optimal path. Because obviously I can build a very convoluted path that has very high cost, and then the change in the heuristic between the states could be very small, because maybe my actual path continues here and comes all the way back to be adjacent, and I don't need to think about like the large costs that I would incur in some very convoluted suboptimal path. So it's just that when I think about in a directed graph particularly, that I want to be saying, well, from some A to B, but I'm reasoning over some convoluted path, I actually have to be reasoning over the optimal path to show that we could do this over the entire state space. Okay, so that's getting a little bit into the weeds, but hopefully this gives you an intuition of what is going on and what is consistency doing. And we're going to use this now, the properties of a heuristic. And for right now, we're only going to assume that our heuristic is consistent. Later on in the course, we're going to come back and say what happens when the heuristic is inconsistent and what is going to happen to our search algorithms. But this concludes our look at consistent heuristics and consistent heuristics, so that we can now build algorithms on top of that.